Welcome back. This is the third lesson in the first unit of BC Calculus, and today we're going to start things off with a warm-up. So you're evaluating the limit as x approaches infinity of this rational function. So go ahead and take a moment to yourself. You can pause the video if you'd like. Okay. So if you remember from the first lesson, we talked about multiplying the numerator and the denominator by 1 over x, or 1 over x squared, and in this case maybe 1 over x cubed, because that would get rid of the x cubed, and everything would sort of simplify to a rational function that we understand about its end behavior. However, if you do remember from Algebra 2 how to find the asymptotes of a rational function, and in this case horizontal asymptotes, then you would know right off the bat that if the exponents, we have exponents here that are the same, the leading exponents are the same, therefore I'm looking at the leading coefficients as my limit. So the answer here should be simply 3/4. So this chapter, we're talking about derivatives. And I know that you've talked a lot about derivatives in pre-calculus, so we're really going to breeze through this next chapter. But I do want to at least spend a little bit of time to talk about some of the subtle nuances of derivatives. So before we really begin talking about derivatives, I want to look at the equation of a tangent line. So in your textbook there's a definition, a great definition. I believe it's in your printed off notes as well. But the definition of the equation of a tangent line. So this is a line tangent to a function. Notice that the equation is the equation of a line, and in this case it's in point-slope form. And the slope, right, the slope of the tangent line comes from a limit definition. Okay? And it's defined as the limit as x approaches x naught of f of x minus x, f of x minus f of x naught over x minus x naught. And all that is really saying is this is just the secant line graphed in green, and I want to take the limit as this x value gets closer to x naught. So as that happens, this line begins to straighten out. Well, it's always straight, begins to become more and more tangent at this point x naught until we have the tangent line. Okay. And then the equation for that tangent line comes from the point slope form of the equation of a line, where the slope is the slope defined here, and the y and x point or coordinates are of that point x naught. So for our first example today, very straightforward. Find the slope of the line tangent to the graph y equals 4x squared at the point 336. Now I know most of you could probably use your shortcut differentiation rules that you learned in pre-calc and solve this rather quickly, but I would like to use the definitions that we just looked at so we can start making some connections, again with those subtle nuances within derivatives. So remember, the slope of a tangent line is a limit. The limit as x approaches x naught, and in this case x naught is 3. Okay? And it was the difference in my y values, which is 4x squared minus, and then f of x naught, which is 36, and then divided by x minus x naught. All right. Now this factors nicely. And we get 4x plus 3, x minus 3, And as we can see, the x minus 3 factors will cancel to 1. And I'm left with the limit as x approaches 3 of 4 times x plus 3, which is 24. So that's the answer to the first part of the question. What's the slope of the line tangent to the graph at the given point? Now we're asked, what's the equation of that line? Well, the equation of a line, we're going to use point-slope form. The point I'm using is 336. Okay. The slope comes next. And we're done. Okay, the next definition I want to look at is average rate of change. It's very similar to the last definition that we looked at. The last definition really focused on the equation of the tangent line, whereas this is more of a, it's the rate of change, the average rate of change of a function, which can be thought of as that slope part of the tangent line. However, the average rate of change typically occurs over an interval. Okay, so for instance, the average rate of change of f of x over the interval x sub 0 to x sub 1, okay, is the slope of this green secant, which is obviously rise over run. The rise being the difference between f of x sub 1 and f of x sub 0, and the run being x sub 1 minus x sub 0. So we get the average rate of change being defined this way. Alright, so in this example, I have a table of values. The column for t represents time or a year, and S of t represents the percentage of senior males who said that they had 1 or more cigarettes a day. So my question is, what would be the meaning of S prime of t? In other words, what would be represented by the derivative of the function described in this table? And what would those units look like? So take a moment to yourself and think. You can pause the video if you'd like. So S prime of t means the derivative of this function. And if the derivative is meant to represent a rate of change, then S prime of t represents the rate at which the percent of smokers changes over a given interval of time. And those units would look like percent per time, or percent of smokers per unit of time. And in this case, that unit is years. So the next question says, describe the rate of change of smokers over the interval from 1978 to 1996. In other words, how has the percentage of smokers changed from the beginning of this data set to the end of this data set? Well, we're going to be using the average rate of change formula, which says that I take the y value, or the range value of the endpoint, minus the initial, and divide by the time interval, 1996 to 1978. All right. And we should get something around negative 0.294. So what does that mean? Well, that means that the average rate of change of the percent of smokers over a given time interval, in this case it's a year, is minus 0.294. So we would expect that every year the percent of smokers would decrease by 0.294%. Okay, let's do an example of using the definition of derivative to find the derivative of a function. And we're looking for the derivative function, not the derivative at a point. So I've gone ahead and written the definition of derivative, or the definition of the derivative function. And we're going to use this formula to find the derivative of f. So I want the limit as h approaches 0 of f of x plus h. So everywhere I see x, I'm plugging in x plus h. Minus f of x, which is just the original function, divided by h. Okay. Now obviously this limit can't be computed by simply plugging in 0 for h, because we get 0 in the denominator, which is undefined. So we are going to have to do a little bit of simplification here. So let's see. Coming up with a common denominator and multiplying by the proper factor, we'll end up with, let's see, x squared plus hx plus x minus h minus 1 minus x squared plus hx minus x plus x squared plus h minus 1. And that's all over that common denominator of x plus h minus 1 times x minus 1. All over h. Okay, well at the top we have a lot of cancellations that are going to occur. I'm going to mark those in a separate color. So we have x squared minus x squared. We have hx minus hx. We have x minus x. X, negative x. Oops. I think that was supposed to be a positive x. Negative x plus x. And the negative 1 minus a negative 1. We're left with negative h minus h. So I'm left with negative 2h all over this denominator all divided by h, or multiplied by 1 over h. Now we can start to see this derivative function take form, and when I plug 0 in for h, I have x minus 1 and x minus 1. So my final answer here is negative 2 over x minus 1 squared. Alright, now the question asks to state the domain of both f of x and f prime of x. Okay. The domain of f of x is the set of x values from the real numbers such that x is not equal to 1. Right? If x is equal to 1, then we have 0 in the denominator. There's a vertical asymptote there. Okay? And let's see. The domain f prime of x is again the real numbers such that x is not equal to 1. Again, x cannot be 1, otherwise we'll have 0 in the denominator. So that's using the definition of derivative to find the derivative function of a given function. One of the more difficult tasks for students to do in BC Calculus is to graph a derivative function given the graph of f of x. So the pink function here is my f of x. And what I'm going to do first, oops, we don't want to do 5 of these, we just want to do 4. I'm going to look at the derivative or the tangent line at a few points. So the slope of the graph at 1 looks to be horizontal, so 0. At 2, it looks to be about 1. At 3, maybe a little less, we'll say 3/4. Again, these are just estimates. And at 4, it looks like we're again at 0. So now, to actually go through and graph the derivative, I have a few points that I can use to plot in my coordinate plane. 1, 0. At x equals 1, the slope of the tangent line of my original function was 0. At 2, it was about 1. At 3, it was a little less. And at 4, I was back to 0. Now I could connect these points and have a nice piece of the derivative function, but we want to graph the entire derivative function. So let's sort of analyze the rest of this pink graph here. Notice that from 4 on, the slope is negative and gets more and more negative or steeper in the negative direction until about this point here. And then it begins to level off and the slope approaches 0. So we're going to get more and more negative until about here, and then start increasing and approach a slope of 0, but never reach it. We're asymptotic to the x-axis. In the beginning, my slope is very, very negative, but quickly becomes 0. Oops. So something like that. Very, very negative slopes, right? Decreasing, or excuse me, increasing, if you will, the magnitude of which is decreasing to 0. and then asymptotic as we go to infinity along the x-axis.